Thank you everyone for being back at Revolutionizing Healthcare. Um, for those of you that are new to Revolutionizing Healthcare, this is actually the fourth year of these engagement sessions run by the Schaar Lab under the leadership of Professor Mihaela van der Schaar. And this is probably one of the most exciting sessions there's ever been, because today we are going to be discussing how clinicians can actually use machine learning themselves and how you can build predictive models without any coding knowledge that you would have to have prior to this. And we're basically going to have this main topic of putting you as the clinicians in the driver's seat of building predictive models with a new tool that we developed in the last few months, which is a no-code AI/machine learning partner that helps clinicians build predictive models. And without further ado, I will hand over to Tim Oosterlinck, who's co-hosting these sessions, to introduce our panel. But just before we do that, just a quick reminder of how these sessions usually run. So it's 1 hour from 4 to 5 British summer time, and we will roughly have 5 sections. After the introduction, we'll have a presentation by Mihaela van der Schaar, who will introduce the vision and the methods behind our new chatbot tool. Then we'll show you an actual demo video of this no-code AI/ML partner tool. And then we'll have a panel discussion with our amazing panelists. And then there will be time for Q&A as well. So any questions that come up for you during the session or that you might bring with you, just put them into the chat or the Q&A chat. You can also upload the most important questions there, and we will take them during the discussion or towards the end of the session. So now I will hand over to Tim Oosterlinck.
Okay, welcome everyone. Let me first start off by introducing our panel. First off, we have Professor Vasilis Kosmoliaptis. He's a professor of transplant surgery and immunology at the University of Cambridge. He's not just a researcher, but also a practicing surgeon, primarily involved in abdominal transplants, hepatobiliary surgery, and endocrine surgeries. He's also one of the select few that got early access to our lab's tools, and he's ready to share his first experiences with us as well. Thank you for joining us. Next, we have Professor Andres Floto. He is director at CCAIM and also professor of respiratory biology at the University of Cambridge. He's also a Wellcome Trust Senior Investigator and Research Director of the Cambridge Center for Lung Inspection at Bayport Hospital in Cambridge. Professor Floto had the chance as well to take our new tool for a spin and also gave a demo during our last Cambridge Summer School. So also thank you for joining us, Professor Floto. And finally, joining us is Dr. Tom Callender. Dr. Callender is a research fellow and a public health physician at UCL, and he's also a senior public health register at the UK National Screening Committee. He's got a food in research and another one in public health and policy world, and he's part of the CCAIM faculty as well. He's bringing his vision to the session today. Thank you for joining us. And with that, I'd like to hand over to Professor Mihaela van der Schaar, who will guide us through her vision for the future. Mihaela, the floor is yours.
And thank you very much, everyone, for joining us. As Tim Schubert has mentioned, this is really for us quite a journey. This is, well, we are starting now the 5th year. So we really hope that you are going to stay with us and help us be inspired and collaborate with us. And today I'm especially excited because, as Tim has mentioned, we are going to present to you a project that we have been building for the last few months in developing and conceiving a virtual partner for clinical researchers. And this is really a tool for the revolutionary clinicians like the ones that are attending this session. Let me start with something that I said very often, that my vision for the future of medicine is to empower you, the clinicians, with tools that could be useful to you. Not tools that somebody is imposing on you, but rather tools that you yourself select and co-develop. tools that will be truly useful to make your life as a clinician better, and also to enable you to better treat the patients in front of you. And I also often say that, like, I would not like to go into a plane without a pilot, a human pilot, as well as technology. In the same way, I really would prefer in the future as a patient to be in front of a clinician that has also a lot of tools at their availability to better cruise through my healthcare profile and best advise me. And you see here one of our collaborators, Professor Owen McKinney, who is working through one of the early demonstrators that we have built a few years back, which is really empowering him to make decisions about time series data. So ideally, everyone should be able to have the co-pilots they need when practicing medicine. So ideally, this AI-empowered clinical ecosystem will be diverse, and each clinician should be able to build or at least select among the variety of analytics that exist for their disposal. And since all of you have different patients, you operate in a different types of clinical ecosystem and may have different needs. Ideally, you would like to have the ability to build your own tools whenever such an opportunity arises and you feel the need of having the help of an AI-empowered tool to help support you. So a key question is, we have had this vision for quite some time. So why is it not happening today? Why is AI still so far away from being prevalent in the clinical space? Well, first, I believe that it remains a quite complex endeavor. From conceiving and defining a clinical problem or a logistics problem in the clinical ecosystem, to modeling it correctly, to validating it, and building demonstrators to review, debug, and test it. All of these phases, which are at the beginning of the journey, because later, if let's say everything is fine, one would still need to go at times through clinical trials or more thorough validation of these tools. But even these preliminary stages where you are having the proof of concept, they are very tedious and time-consuming. In collaborations with a variety of clinicians throughout the world in 3 different continents and numerous clinicians in various disciplines, I've seen the pain of co-developing together with them this process. And the reality is that at every stage, there is a particular challenge. And there is a lot lost also in the translation between the clinician and us, the machine learners. So while we may want to build these machine learning powered tools and put them in the hands of you, the reality is that we don't scale. And also your time is often limited in developing such tools. So often projects take a very long time and they often fall through the cracks. So the reality is that this is hard. Early on in the journey, I was believing that this is a hard task because there are many modeling choices which machine learning offers. So machine learning is not just one tool, it's a variety of tools, at times interlinked. Many of these tools have parameters and hyperparameters that need to be instantiated correctly. And also how to model a particular problem, real-world clinical problem, allows for different types of variants. Finally, even if we are building a correct model, you will need to debug it at length to make sure that this is indeed useful to you through model interpretation. So it is an entire pipeline that involves many tasks, many variables. You may need it for different reasons. Again, somebody may want to build a clinical risk score, while somebody else may want to predict whether they are going to have a particular blood supply available to them when they'll do the next intervention. So very different needs, also, the world of machine learning is very alive, like the world of medicine, and we continue to build new methods and new ideas, and selecting among them the most useful tool is at times challenging. So what we envisioned quite a few years back was to let machine learning itself do the crafting of these machine learning models. So we were very active early on in the field of automated machine learning, where we use machine learning to do the crafting of the machine learning models upon a given specification. So since 2017, we have built automated machine learning frameworks for a variety of analytics, including prognostic models that are interpretable. And early on, together with the former student Ahmed Allah, we built the first AutoML framework for clinical scores, which was not just a classification tool, but really did much more, did entire pipelines, dealt with missing data imputation, feature processing, classification, and calibration, issued predictions as well as explanations, and through a process called meta-learning was able to learn from complementary cohorts. And then together with collaborators, we went and started to use this tool in numerous applications. With Janet Allen and Andres Flotto on cystic fibrosis, and then cardiovascular disease, prostate cancer, and many, many others. Here is just a small subset. We also used it as the first tool in COVID-19 to predict the use of ventilators and hospital beds. Also, this was a tool that early on was used on UK Biobank, which is a very powerful resource. This was one of the first tools ever applied, first AI tools ever applied to UK Biobank. We have done it on cardiovascular disease, and this enabled us to really understand whether certain variables are important and whether we can discover new risk factors that the clinicians didn't know, whether we could improve on top of well-known risk scores you are currently using in the medical practice, and identify, for instance, in this case, the diabetics as being a subpopulation for which is really a need for a new risk score. So my guess is many of you, as you practice medicine, may have a particular specialty or a particular issue that you see improving, that the need for improvement, and hence you may want to use whatever data you may have available, whether in registries, biobanks, or maybe locally in the hospital, and see if you can build, using machine learning, an improved score. And in that pursuit, we went further and we didn't build only AutoML for classification, but also for survival analysis, time to event analysis, time series data. We built tools for data processing like imputation, individualized treatment effects as well. So you would say, we are done. This is what I thought when I finished this project. And then very fast, I realized that this is not enough. This was not enough, first, because this project was not really conceived together with a clinician at our side. So in Autoprognosis 2.0, my former postdoc, Fergus Imrie, joined forces with me and a clinical collaborator, Professor Owen McKinney, to really think together with him how such a tool would be used in practice. This project also benefited from an excellent machine learning engineer, Bogdan Cevere, who also improved significantly the code base beyond what we were able to do in the initial autoprognosis. So this work, Autoprognosis 2.0, is a lot more refined, is a lot more easy to use. The software is a lot more easy to use. It has user interfaces, and also take the vision of in making it more useful for a clinician. For instance, it also contains many more algorithms and ways to interpret the predictions. The user interfaces are very good, and also the Python code that came associated with this project, and they can be easily downloadable, was produced. Very high quality software, and also we put numerous tutorials by various clinicians that have used this autoprognosis. So we thought, we are going to accomplish quite a lot with this. And the reality is that while some of you, the revolutionary clinicians, have taken this tool and use it in a variety of settings, still the uptake is limited. So then I thought, well, maybe it's a question of just specifying more clearly why AutoML is useful. So together with Tom Callender, we wrote a paper in Lancet to try to explain to the community that AutoML are tools that could provide a lot of help for the clinicians. They are easy in deployment, often they are open source. You can easily build tools for many diseases. You can determine what is the valuable information and the valuable covariates for making a particular forecast, so such that in the future you don't need to collect all the many variables, but rather a subset. Also, these tools would allow you to see what's the value of modeling, machine learning, as opposed to more conventional linear models well known in statistics. These models also allow us to have uncertainty estimates such that you know when the tool is trustworthy and when it's not. And they can be also non-stop updated through a continuous learning process where we can incorporate up-to-date machine learning tools. But this still didn't do it. And then we started really at the beginning of this year to reflect why not. And the reality is that we realized that AutoML is only a partial solution. While it enables optimization of model building, still required a lot of technical expertise, including you becoming familiar with Python, which a few of our revolutionary clinicians that became collaborators started to do. But the reality is many of you don't want to code, and for good reasons. You have many other things to worry about than this. Also, another reality besides the need for coding was the fact that we realized there is a lot of time spent not only in building the predictors and the classification methods or the analytics, but also in the data. Very often you had complex data sets that you would bring to these automated tools, and the data was not perfect. It had all sorts of errors. It had all sorts of missingness. Often you were yourself surprised by what is in your data, partially because over the years you have collaborated with machine learners or statisticians or other people who dealt with your data. At times, some of you were surprised by what is in the data that you thought you knew quite well. At times there were errors in coding. At other times there were variables that were collected for a different purpose. At other times there were variables that were telling us what the prediction will be. So it didn't need to be included to provide leakage in our analytics. So really, we realized that you need tools to explore and better understand the data that you want to incorporate into these analytics. And such tools were not built in. And finally, whether it is for understanding the data and understanding the type of data, the outliers in the data, as well as the outputs of the analytics, you needed better intuitive interfaces. So with this in mind, we joined forces. So Evgeny Savelyev is a machine learning engineer in our lab. Tim Schubert, you already know. Thomas Paplin is a PhD student in my lab. And we had the good fortune to have Vasilis, who really got very engaged with us and with this tool. So using him as our prototypical revolutionary clinician, we try to build a tool for somebody like him. And Vasilis is one of the few people who can code Python, one of the very few surgeons that I think can Python code, but we oblige him not to. We oblige him to be playing a different role, the role of a surgeon that would like to be engaged in this tool and its building, but one that will build this tool for others in the clinical domain that may not have his technical knowledge. So what does CCAIM do? this is an AI-enabled virtual partner. We call it a partner rather than a copilot because the reality is, unlike other copilots that are being built, what you see here is more of a partner for clinical researchers to build predictive modeling. So what you see on the left side is the clinician coming with a data set and a problem, a goal they want to achieve. And then using CLIMB as a partner to really support them in building a predictive model by going through all the steps of data exploration, data engineering, model building, and model exploitation. And this is not done just once. This is done through an iterative approach, which involves visualization of what has been done, summary reports, and refinement all the way till the clinician is satisfied with what is achieved. To build CLIMB, we have really developed quite a lot of machine learning. We built on powerful large language models, where we also had quite a lot of support from Microsoft Research and Microsoft in general. And we use large language models to build reasoning units that are very dedicated to building such a copilot, because it is not only a question of let's say, invoking this copilot for help, but also thinking step by step in a way in which even the most recent bots are not able to do. To be able to think through the pipeline of analytics to allow for such predictive models to be built. And again, here, the planning and the feedback that our reasoning using takes is really very much integrated as a response to what the clinician needs and the feedback that the clinician gives. So this is a very different types of reasoning, a supportive reasoning for the clinician. This is why also we call it a partner. We added, in addition to the conventional autoprognosis, a lot more data-centric tools, because as I mentioned, what we realize, it is not only about building analytics, but also understanding the data, visualizing the data, selecting the data. And this is a very important first step prior to just building the analytics. And finally, we spend more time on trying to build post-hoc interpretability to allow you to debug what you have built. So you are going to see from Team Schubert very soon a demonstration of CLIMB, but I just want to anchor your idea that first we have this exploratory data analysis where the focus is really to build tools that allow you to see the statistics of the data that you have, the dependencies between the data you have, the missingness that you have. And this is, I think, very important because now, even if you don't want to build analytics, machine learning, or statistics, you can use CLIMB just to understand your data, which I think will be very exciting and very powerful for some of you. Also, you can do easy data transformations because there could be variables that, for instance, need changing, or you want to really aggregate columns or do some type of data transformation to improve or change the data set that you currently have. In the future, we are also going to build tools that allow you to harmonize different types of data sets. For instance, data sets from different types of trials, or a trial and a particular observational data. Then we have the more mature automated machine learning frameworks like autoprognosis. Many of you have seen that in previous Revolutionizing Healthcare sessions, and if you didn't, please look back at some of our past sessions. And finally, we have quite a lot of interpretability tools as well. You see here on the right side the feature importance, which tells what features were deemed to be important for this particular predictor that you can use to debug the tool that you have built. Now, CLIMB, as opposed to a baseline ChatGPT-4, has quite a lot of advantages. In addition to being flexible in terms of adaptation to your user prompts and user feedback, it has a very robust planning, enhanced memory, access to external tools, data-centric tools, as well as machine learning tools, as well as visualization tools that ChatGPT-4 does not have. It has an informative dashboard, and we plan to spend additional time in the future to make that even more useful. And last but not least, privacy, because you may not want to have your data being seen by ChatGPT-4, and CLIMB allows you to keep your data private. In a short poll that we have taken during our summer school earlier this month, actually earlier last month, we have seen that indeed CLIMB seems to be preferred to ChatGPT-4 for the task of building analytics, and you can see here the reasons behind that. So what are our next steps? We would like in the next few months, hopefully in the next month, to open source our Copilot such that you and others, but also others in the machine learning field, can build on our Copilot and add new tools and build new, let's say, the entire environment to make it more useful for a variety of uses, not only prediction. So one particular topic that is very interesting to us in our own lab, given the fact that we don't build just predictive analytics, we would like to look at time series data as well as causal inference. Also, together with a few collaborators, we plan to look at 3 different subsequent usage of this Copilot. We want, together with Andres Flotto, to look at cystic fibrosis, with Thomas Callender to look at population health, and also we are very interested in the complexity of hospital care and building analytics for that. So my challenge before I finish, I want to really put a challenge to you. After we are putting this chatbots and this the CLIMB in the public domain, why not start building your own analytics? I really hope that this time it will happen. I hope that you are going to start to use CLIMB, whether it is to visualize the data or build the first analytics, or why not refine your current analytics with the help of CLIMB for your medical profession. Thank you.
Thank you so much, Mihaela, for that great introduction. So while Evgeny is pulling up the videos, just one thing to note, because there have already been questions in the chat about potentially creating method sections. Actually, this is the beauty of it, right? Because it has a predefined plan that it will guide you through, but in addition, it will also allow you to do specific things that you're interested in, and it can adapt to your own plans or your own interests along the way. So we will actually show you a bit of what Mihaela has shown you in these few figures, but just as an actual demo of the tool itself. And we will get started in the data exploration stage. And at this point, some rows have already been removed because they were not meaningful for the data set. So we're basically starting from that stage, but this is very early on in the pipeline. So now I will not talk too much such that you can also focus on the video, but I will just anchor you a bit in what is happening. One thing to bear in mind, there's going to be a bit of scrolling up and down. That's just basically a user interface bug, but it shouldn't impair any of this too much. So Evgeny, if you would like to see the video.
Yep, there we go.
Okay, so at the very beginning, the dataset has been loaded in, and now descriptive statistics have been generated, and this is all very fast. If it's too fast, don't worry, the paper will actually be out at midnight, so you can watch these videos again. But basically what it will provide you with is quite a thorough dataset overview. So you see on the right-hand side, this is the plan that CLIMB guides you through. And you can see which stages we're currently in and what stages have been completed. On the left side, you can see the chat itself. And you can actually view any code or any output that has been generated. So quite a lot of descriptive statistics here. And in just a minute, these will also be summarized in neat plots. You can see here's correlation between different variables in the data set that we use. There's also explanations as to what you actually see. And these files that are being generated can also be viewed on the right. So now it asks us, do we want to create descriptive statistics? And yes, of course, we want to. So let's have a look at that. So you can see it will actually create the appropriate plots for each of the variables. And you can see on the right-hand side in the working directory that it starts filling up with those. And you will see in just a minute that CLIMB itself will actually choose what it thinks to be the most important variables to see. And it says that it will give you the 5 most important plots. So it's basically just inferring that from the data set, what you will probably be most interested in. You can see these plots here. But in addition, all of the plots that have been generated can be viewed from the working directory. On the right-hand side, you can actually look at the distributions for any of the variables. Okay, brilliant. So this was from the data exploration stage of things, as you can also see from the plan. And I think we're ready to move on to the next stage, which will be actual data transformations. So now we are in the data engineering stage. And again, if you could just pause there for a minute. We are at the stage where a few things have already been done to the data, but right now we want to handle missing values. This is obviously very important for machine learning, that you can't have your data set full of missing values, and then there are different options. You can drop rows, you can drop columns, or you can impute missing values. And in this case, what we want to show here is that it is actually Vasilis' data, who's also here on the panel today. And Vasilis had quite specific things he wanted to do to the EGFR 12 column, which you can see here. And this is obviously not something that's done by CLIMB as a standard. So it will generate custom code for that. And Evgeny, please roll. Thank you. So you can see it is explaining what it aims to do with its code first, and then it will generate code using Python. What's also going to be really helpful is that now that the files have been changed, there will be a modified data set, but you can actually view any changes that have been made to the data itself in a data transformations tab, which will be on the right. So this is where you can now select the file, and then you will be able to view any transformations made to the data, and they will actually be highlighted. So in just a second, you will see one of the values has been changed there. So it is all very transparent and interpretable. Thank you. And I think we can move on to the third stage that we wanted to show, which is the model building stage itself. So this is the stage where all data has already been prepared, and now we will run Autoprognosis 2.0. This is a regression study, and yeah, Evgeny, feel free to start the video. Thanks. So what it will do now is it will query this automated machine learning pipeline that Mihaela has already talked about briefly. And Autoprognosis 2.0, what it actually does is it will run many different model types. And then at the end, it will basically optimize and choose the best model and the best hyperparameters. And it will also provide you with performance metrics for the model that is actually created in the end. So you can see that this has already completed successfully. It may take a bit longer if you don't have a workhorse machine like Evgeny does, but it should usually run quite smoothly. And now that we have this regression study done, one of the next things we can do is we can understand which features of our data set are actually the most predictive for our regression study. And this will happen in just a minute. So this is something that we put more in the model exploitation stage, because now the model has been built, and now we can basically interpret the model and different things to it. And we will look at feature importance using another tool, which is called Schaar Explainer. Actually, it's the permutation explainer tool in this case. And it will just give you a summary of which features were the most predictive. So what you can see here is basically Climb doesn't only have the typical LLM capabilities, can generate code, etc. It can also query other libraries and tools like autoprognosis, or in this case, permutation explainer, and it actually has a lot of others under the hood as well. Okay, before we go onto subgroup analysis, which we will not show here today, let's just have another look at the plots, which will show you which of the features were most predictive. So in this case, it is donor sex that is most predictive for for EGFR 12 prediction. So this is just a small or a short overview of what this tool can potentially do, and there's much, much more to do. And to get a better insight, feel free to read the paper, which will be on arXiv very shortly, and we will actually send the link around with the next email. And that will also include at least 3 videos as demos already to have a look at. And we plan to also make more in-depth tutorials on how to use Climb to give you guidance in the future. And we really do hope that you will use this once it's open sourced and create your own predictive models and use them to actually change medicine for the better. Thank you so much for the attention on this, and I will hand it back to Mihaela.
Before you give it back to me, I'll give it back to you. There were many great questions in the chat, but one of them I really want you to take live, which is the question about the from JJ Kim, who is asking what will happen. You are building this compiler, but if you want to write afterwards the method section of your paper, how will you do that?
Oh, yes. So this is actually something that is, again, the beauty of this, that it's iterative. It works with natural language, and you can just ask it, please provide a paper-style method section for the machine learning study you just ran. And we actually tried this before. It works quite well. Of course, we don't want to generate random papers and just throw them out, but it is extremely helpful in interpreting what has been done and putting that into something that you could almost already put into a method section. And of course, you will want to check that first.
Yes, so you will be able to do, for instance, all the statistics that you have developed together with the tool. You can save the pictures. You can also, if you use machine learning method, the information about the machine learning method is available. So all of that is available to you. So it's a question of taking it and put it in the paper, or using a draft, or requesting the tool to build an initial draft, which
Exactly.
you probably will need to check.
Yeah, and the good thing about it is also that really this doesn't just do random LLM stuff, but it actually uses tools and packages that have been quite well described, so you can reference those as well. For example, if you're using autoprognosis, you'll be able to simply reference the autoprognosis paper, and it will be quite easy to generate a method section from all of what is happening here.
Okay, without further ado, Vasilis, you have been very much a partner in crime here, and we have spent numerous nights with you after surgery trying to co-develop this. So Vasilis, please tell us a good and a bad. What are you excited about in this tool on the positive, and also on the negative? What do you think it's next, and what do you think needs to be done better, and what do you think is the road ahead?
Well, thank you very much, Mihaela, for involving me in this work. I don't say that often, but I'm really excited about it. I mean, I think you presented all the various advances and the concepts very well. Perhaps I could emphasize three things. The first one is that it's really easy to use, and that it allows the user to have control. And for me, that's crucial. So you can interrogate your data, you can ask advice about how to analyze your data. You can see what exactly is happening. You can spot mistakes, which are easy to make, especially when you use automated tools. You don't have to worry about assumptions that may be, made from an automated software. So you can interrogate your data, you can understand, be in the driving seat, which is very important. Secondly, it's open source, which I think is fantastic. And thirdly, it really hits the mark when it comes to confidentiality of data. So if you want a clinical tool, it makes most people very nervous to submit clinical data sets onto a server, and then the data being used in ways that you might not be able to control or understand. So these are three very important things that can make this easy to use and very applicable. In terms of next steps, I guess the most important thing is for people to use it. As you mentioned, there's going to be more tools integrated, which is also important. It democratizes, as you love to say, machine learning, and I think it really hits the mark when it comes to that.
Thank you, Vasilis. Let me now put on the spot Andres, who has been an equal collaborator on this. As a matter of fact, we started the work on autoprognosis many years back with Janet Allen and Andres throwing at us this challenge. And you have tried also the tool, Andres. Cystic fibrosis is a tricky disease. The variables are numerous. And the questions that you and your clinical colleagues are putting are often very diverse. I've learned at the beginning of the journey of collaborating that at times you are interested in anomalies, at times you are interested in the few people that are going to do badly, or the few people who are going to. What do you feel that's special and different, and what would be the needs you see from this type of tools to be really useful for cystic fibrosis?
Well, Mihaela, I mean, just to reiterate what Vasilis mentioned, I think this is terrific and will allow a huge number of very intelligent, insightful clinicians who've been pondering questions to start interrogating the data in a meaningful way. And I think even now, just looking at the predictive tasks, it will open up a huge amount of hypothesis generation and excitement in the field. So I think it's already super cool. I think with the planned introduction of the other modules, I think it will begin to address nearly all, if not all, of the kind of current very sexy questions around cystic fibrosis management, but also kind of biomedicine. So I think you'll find you'll be pushing against an open door, or rather you'll be stopping hordes of clinicians from wanting to use it. So I think it's super cool. I think there are some simple cosmetic things that you might want to consider with the interface, which may be slightly off-putting for the non-technical clinicians, but this is cosmetic. The other thing which I know you've begun to do, and I think it does to some extent, is to begin to maybe understand is the wrong word, but appreciate what the features actually are, and to be able to give some interpretation of the relationships that that it identifies between features and outcomes. And I think that while you may argue is the role of the domain expert, actually, I think would be incredibly helpful to explore more. And I know you're doing that already, so I'll stop.
Andres, before you go, one more thing. The cystic fibrosis area is in many countries is very fortunate because you have put across different countries these registries in place, which I don't know they exist in other diseases, but I think cystic fibrosis has done a tremendous amount to have these amazing registries in all the countries that I know of. Do you see anything special that's needed to deal with registry data and to deal with the fact that the data has been changing over the years a lot and the medications have been changing a lot? Do you think anything special is needed to empower your colleagues to use such tools?
Yeah, so maybe I would maybe make 3 points here. That the first is that the genetics are clearly important, right? It's in terms of Mendelian disease, there are lots and lots of different gene mutations. And I think being able to bolt on some sensible way of integrating the genetics in a meaningful way, or interpreting the impact of the genetics in a meaningful way, will be very useful. The second thing is, as you mentioned, the way in which you might standardize or integrate different data sets from one place to another one, and potentially utilize or leverage the enormous advances that your group have made and others in transfer learning in order to be able to leverage large data sets to inform countries with very small populations of cystic fibrosis around policy and management. So I think those are the kind of areas which might be worth thinking about.
Final question to you, Tom. What we have tried to do with this copilot is replace you. You are irreplaceable, so you know this is just a joke. But you and I spend quite a lot of time, and you spend a lot of time, but even I, in making this paper that we did with autoprognosis for lung cancer. And I thought it was very exciting because you put for the first time this question of what's the minimum number of variables I want to see to be able to build a successful risk prediction score. Do you see a possibility that these copilots are now used for people to determine what is the relevant information in screening programs, in public health? Where do you see this type of tool being useful in public health in the future?
Well, I mean, I'm clearly going to be very excited by any of these tools. From a public health perspective, I think they're extremely valuable because the one thing that public health often has is some form of data. I mean, Deepa in the chat has put some stuff about integrated care boards, which are kind of regional health units, and some of the public health problems that are being faced by the NHS and how you might deal with it. One of the challenges, though, in most of these situations is the ability to merge those individuals who are dealing with this stuff at the coalface with the tools that you might need. But more importantly, I think that this will do it in a way that allows you to enhance quality over time. Clearly, you can automate bits and pieces, and people may not know exactly what's happening under the hood, but this, by being so interactive, gives you much more granular ability to understand your data. And I hope over time we can use it to support people to ask the right questions. Because as we get to the point where AutoML, for want of a better word, is capable of doing most of the analytics, then the real kind of selling point for the clinicians and the people who are doing the work on the ground is to think through how best we can use the data we have to solve the relevant task. And this kind of thing may actually help us to think out of the box, because it does leverage some of the LLM ability to be able to think, well, what about these kind of approaches? And I think within a clinical environment, this is really important because some of the problems that we have is not necessarily that people don't build models. There are hundreds of models for most problems. It's that either they're not very well built, they're not validated, etc. Whereas when you have something like this, well, a lot of those excuses disappear. You have to focus on, okay, what's the right question? Building the model is now easy. So it's a little bit more like, okay, I want to order my Uber. I want to know where I'm going. I don't really care about the car and the mechanics of it. I want to get there. And so this is the question that can hopefully guide us to build better models at the right place, at the right time for the right problem, and do it in environments where people may not be filled to the gunnels with people with masters and PhD level data science.
Thank you, Tom. So brilliant insights already. I will also ask Tim O again a bit on the spot, because he's been one of the clinicians in the lab who has used both autoprognosis and also been one of the first ones to debug this new tool. So Tim, could you just maybe briefly share how your experience was trying to get the hang of autoprognosis and then using this instead?
Yeah, sure. So I have been working on a kidney data set for a few months, cranking away with it, using autoprognosis. And I'll be honest, for somebody without a previous coding experience, it was pretty hard. I had a lot of help from Tom Callender. Thank you for that, by the way. But even with his help, it was still very challenging, and it gave me good insights in how difficult it is for us clinicians without a technical background in machine learning to start really innovating with these tools. And when I first started to use this tool, it felt a bit like using ChatGPT for the first time. I think we can all relate that it was really amazing when you started chatting to ChatGPT for the first time, and it felt that way to me as well. And even in the first tries, the model ran a very good, solid analysis of my data already. And as it continued to develop, the subsequent models got better and better and started to give me really amazing insights into my data. So I think this proved to me that this has huge potential to bridge the technical gap that we have right now. And I'm very excited to share it with you more during the coming months.
Thank you, Tim. So before we jump into the Q&A, one other question I will probably ask Vasilis first again is, so we've heard a bit about this tool today and about how great it is, but where do you see the main limitation? What is still needed? What should we still address to make this usable?
Well, I think it's already very usable. One of the things we haven't sort of mentioned specifically is that it can make you very productive. And I think that's a huge roadblock for most clinicians or non-experts. So now, as Tom was saying, you can get from A to B. You can ask the questions you want without sort of trying to collaborate with 3 statisticians and 2 mathematicians, and you can get an understanding of your data, which can make you far more productive. The risk I feel with any machine learning, especially automated machine learning software, is how you use it. We discussed in the interactions we had, writing this paper, about your ambition to have sort of to allow the clinician to, without specific domain knowledge, to ask questions. But you really need to be careful how you use it. It makes it easy, but you really need to be in a position to understand your data, ask the right questions, handle your data, like the missing data, the EGFR12 example you mentioned, in the right way. And you can see how easily you can make mistakes, and you can derive the wrong model, and you can publish the wrong model. It's very difficult then to interrogate that. So my fear, if you like, with the expansion of using machine learning, especially automated tools, is how it's going to be used and what we'll see out there. We need some safeguards in terms of quality. I'm sure all the rest will happen. More tools, better tools, etc., will happen organically.
Thank you.
in that case, I think we can move on to the QA session. And I think I would like to highlight a question from Reza about the privacy concerns. So I'll maybe just ask you to mute yourself, and you can ask it to Tim S.
Timo, maybe you can read it.
I will just. All right. So Reza was wondering what it would mean for the privacy of her own projects. Do we need to upload the data, or is there a local app where we can download it?
Okay, thank you for that question. So first of all, different clinicians using this tool will have different privacy requirements, and you, as the people who hold the data, as basically the data stewards, will be the ones who know which basically which requirements you have. So that will be very important. What we can definitely do is explain how the tool itself has privacy features. So first of all code is executed locally, all files are stored locally, and the LLM that is being used on secure Azure servers, which have specific privacy features as well. And actually also only summary statistics are shared with the LLM, even though it's already run on private instances, as far as I know. But Evgeny can add more to the technical details on that.
Yep. Hello, everyone. I'm Evgeny. I wrote the code for this tool. So yes, the privacy is obviously a very important question, especially in the medical field, and everyone always wants to understand this. But as Tim says, the most important thing, first of all, is to know what the privacy requirements of your data are. And the second thing is you need to understand what the tool does with the data. And the key points, all the code that's executed and all the tools that are executed, they will run on the machine that you are running the tool on. So either your workstation or computer or laptop or your local server. The language model, you need to connect with a language model. And the way we have been doing it so far with help from Microsoft partnership is to deploy this language model on Azure secure servers. And they have very specific privacy points. For example, the data is not used to improve any models. The data is not used to improve their customer experience or retrain the model or anything like that. It doesn't go to OpenAI, even though these are originally OpenAI models, right? We're using a version of GPT-4 right now. And another thing is that with Azure, what you can do is you can specifically apply for a specific exception where no human will see any chat interaction between you and LLM under any conditions, because normally there is an additional restriction about human manual review in case they suspect some dangerous activity. But with that exception, you can make it into a situation where no human will ever review it if you get the special exception. And I think that's the most private setup that you can have at the moment with the most powerful LLMs. Like if you did it directly with OpenAI, for example, there's almost no privacy guarantees there by comparison.
Thanks. And just one thing to highlight, CLIMB is modular, so in the future you could also use locally deployed LLMs, for example, if that's
exactly right
situation. Okay, thank you. Let's move on to the next questions.
Yes. So we had another question. I'm trying to find who asked it, but it was about being able to have a chain of thought and to have other models within the tool critiquing itself. I'm not sure who you were, but you can ask it live if you want as well. But that's in the tool as well.
Would you like that? Would you like? I think J.J. Kim has asked this question. I don't know whether he's online. If he's not, I can try to answer it. So also, as I mentioned, right now we have a planning module. This planning module uses some type of reinforcement learning to be able to plan. Again, the area of planning and planning given feedback and complex planning given feedback is still very much a research area. So we are going to open source this package with a particular planning tool that we have implemented, but we hope that others, in addition to us, are going to keep improving on this particular component, which we think is very vital. And we ourselves in the lab are going to continue to improve on top of it. And this is on top, if you like, it's an improvement on top of what chain of thought currently can offer.
Okay, thank you. German has his hand raised as well, so feel free to ask it live.
Thank you so much. I'm Herman. I'm actually an infectious disease practitioner here at Houston, from University of Texas. And I have a question in terms of I think I raised this question during the summer school. I was wondering, once this package is going to be released, for the survival analysis, are you going to have the option for competitive risk?
Mihaela, do you want to go on that?
Yes, I want to go on that. So thank you for this question. Very, very good question. So we do have tools for competing risks, but they are not currently in this tool. So slowly, so I can point you out right now to tools that we have in machine learning for competing risks that you can use, but you will need to use Python to be able to interface with them. It is on our list to bring competing risks because we know that many of you are interested in that in the future, but the current model can only do time to event analysis to one type of event. So we do not have competing risks, but we plan to add them in the future. And if you are interested, we can point you out to current implementations, but not in this Copilot.
Yeah,
Oh,
just about
fantastic.
open
Fantastic.
sourcing as well. I can.
Fantastic.
Oh.
If you can point me to that info, because I'm very interested. I'm interested in transplant ID, infectious disease, so I'm kind of playing with that.
We will open source it this month as well. That was the other question.
Okay, I think we have another hand raised from Neil.
Hi, everyone.
Hi.
Hi, nice to meet you. I'm Neil. I'm a neurologist at Imperial. Amazing to hear about some of the work you've been doing. This looks so impressive, and I wish I'd had it during my PhD. It would make life a lot easier. So I just wanted to ask a question about the kind of the extent to which these models, to the extent to which like the basic arithmetic operations are done by like an LLM in a kind of weird probabilistic way versus like in Python or R. And are you confident that like reliably 1 + 1 is 2? I'm sure you've thought about that, but I guess this kind of comes up in other contexts and some of the things that I've been thinking about using these for. And how do you know that? And yeah, it'd be useful for me to know the answer as well.
Jenny, why don't you jump?
Yeah. I can explain. So the way we handle this is that absolutely no. So arithmetic operations and anything like that and is not done by the LLM at all. What is done by the LLM is two things. One, it can summon a tool, a Python library that we've written, one of many that we have integrated with Climb, and that tool will run on your computer. And that's obviously all been tested, all the models, it's all well understood that there are no, that's actual Python library code. It's not LLM hallucination, not involved there. And the other thing that the LLM can do, it can generate some code, which obviously is stochastic, right? It can generate some code, and that code will be executed on your computer, but we sort of limit to when it does that. And we limit it to tasks that they are better at, which is mainly manipulation of data in the beginning, not creating models from scratch, because then it becomes much more unreliable. So hopefully that helps. And you can review the code, and you can also review what has happened to your data, as you've seen in the video. You can see what has been changed and so on. So we're trying to keep it as transparent as possible in that way.
Yeah, that's really helpful. Thank you. And I was experimenting with using sort of GPT-4o to run some kind of questionnaires, where you sort of ask like 10 questions, and if you answer A, B, C, or D, you get 1 to 4, and then it adds up the total score at the end. Kind of trivial stuff like that. But it'd be interesting, perhaps at another point, to hear your thoughts about the ability of some of these models themselves to add up reliably and how well they do it. But it sounds much safer to be using some other other tool to do so. Thanks.
If
Yeah, go on.
Vasilis, please go.
If I can take up this point a little bit, I think as part of expanding this paper, one of the useful things to do is to compare the tool and its algorithms implemented with a domain expert. So you will use your data and have a domain expert run, say, statistical analysis, a survival model, whatever it might be, using a large data set, versus how CLIMB performs. And this will allow you to compare and validate the accuracy of the model and of the software. And I think we need to do that.
Yeah, it looks really impressive. So thanks very much.
Okay, thank you.
Okay. I think we'll wrap up the Q&A here. In the interest of time, I'll maybe throw it to Tim one last time.
Yeah, so just briefly, I've already put this into the chat, but we're still finalizing CLIMB, so it does exist, it's ready, but we want to polish it before we actually open source it. And we want to make sure that everything that you will want it to do is sort of in there as much as we can. So we have a little questionnaire, and I will just put that into the chat again. So if you could fill that out, that would be tremendously helpful to us to just understand what kind of prompts or questions you would like to give to this kind of tool in the different stages that we talked about today and that you saw in the videos. So anything, any feedback, any ideas you can put into that would be tremendously helpful to us. We'll also send this link around in email, and again, it's just a brief form, won't take long to fill out. That would be amazing. Thank you so much. And I'll hand it back to Tim to conclude this really interesting Revolutionizing Healthcare session.
Thank you, Tim. And before we wrap up, I'd like to invite you all to join us for our upcoming sessions. On the 5th of November, we have a session diving into digital twins, and we're really excited about that session and have brought some brilliant minds to you to introduce you to this concept. And then on the 3rd of December, we'll be discussing the progress in AI education for clinicians, focusing on how we're adapting training for this evolving landscape of machine learning and medicine. And we'd love for you to be part of these conversations. And we also encourage you to invite your colleagues as well. And they can sign up using this QR code or through our sign up page. I would like to thank our panelists and everybody for joining us today. And we look forward to seeing you again next session.
And Tim Oosterlinck, if you allow me, there are many questions where this session can be found. If you are subscribed to our sessions, you'll receive it through email, but you can find this session as well as the sessions over the last 4 years on our website that's highlighted here, Van der Schaar Lab Engagement Sessions, Revolutionizing Healthcare. So please take a look also at older sessions, which may be relevant to you. We talked about competing risks in some cases. We talk about other topics that you raised, so that may be useful for you to just listen to. Thank you.